What we are focusing on is exactly what's the next big thing in AI. In our core belief, it's going to be way more on pictures, on audio, on all these kind of things. We want to have a better us. We want to have a better human that basically replaces some of the hard works that we do on a daily life with the human intelligence. We see that the way we compute is much more compatible to solve very fast these pictorial-driven AI cases, and for instance, realizing text to instantaneously video. You write your plot and instantaneously your movie is generated. Other imaginations. How about if you had an infinite game where you decide what the next steps in the games are and an AI is just generating the game?
Hello and welcome to Let's Talk About Tech, your podcast on venture capital and private equity, brought to you by Venionaire Capital, the entrepreneurial partners. Today, it's my great pleasure to introduce you to the CEO and founder of Q.ANT, a German-based photonic computing company, and in my humble opinion, as a friendly co-investor, the world leader in photonic computing. Welcome, Michael.
Welcome, Berthold.
It's amazing to have you here in Vienna. I know it's not your first time. We've spoken a bit before, and there's many scientists you know here. And as I know, you have a scientific background. Tell us a bit your story, how you became an entrepreneur.
That's a long story.
We have time.
Okay, that's typically when I try to reflect how it came to the foundation of Q.ANT, I typically start pretty early with my first computer at the age of 4 or 5 aroundish. It was an Amiga 500. You might know it. And this was when I fell basically in love with computers, with the digital industry, with coding and all these kind of things. And this joy basically I've preserved throughout my life. And at the age of 18, I thought there's more. There must be something outside of coding, computer, and so on. And that's why I started studying math and physics. Pretty soon fell in love with quantum information science. That's also where then I basically did my PhD. And this is also, because you mentioned it at your intro, how the relation to Vienna came. Because Vienna at itself, at the university here, is outstanding in terms of quantum science. And it was in the year 2012 when I was nearly at the finishing of my PhD. I met a professor here, and jointly the idea was born at the so-called QCMC conference that we should have a joint project together with NIST in Boulder. And this was basically when I moved to the US for 2 years, did a postdoc, if I may say so, there. And back the time, I thought I'll become a professor for quantum information science. But throughout this postdoc area, I would say that the idea, or there was basically always this inner feeling, yes, science is great. It's great to do the publication. It's great to research. But what's actually happening with that research? And in 2014, I decided that there must be more than just doing research and writing paper. I mean, this is a great, it's a great job. And I thought founding a first company. Not that I was prepared for this and not that I succeeded. But I learned that there is more than just having an idea. And there's more to learn outside of technology. And that was then the decision that I said, okay, I want to pursue on this route. But first, I need to get some experience in industry. This is where I basically then switched to consultancy, where I came to the company Trumpf and learned Peter Leibinger. I got to know Peter Leibinger. And he actually gave me, the chance because he felt that I then was prepared on the one side from the economics point of view. And he read one of my studies and said, I think you should found your company. You're much more an entrepreneur than a manager. I'll become your first investor. And this was around about 2017 then. This is where the idea Q.ANT was born. And the great thing is that back then in 2017, the fundament technology and the idea was to do data processing with light instead of electronics. And this was how it came to the foundation. And this route we've pursued since you joined this year as an investor.
Pretty cool. I'm sure there's maybe one or two people out there that don't have a physics PhD. Would you mind explaining what quantum information science is in very simple terms? Maybe somebody starts studying physics after that.
Information science in general is that you generate, you process, and you make data visible as a result, and this is typically done with regular math. Now, if you, instead of regular math, as we learn it at school, use quantum mechanics, then this is called quantum information processing. So it's basically the combination of quantum mechanics and regular data processing. You take advantages of the special phenomena of quantum mechanics, for instance, like superposition or entanglement. Not that I expect that this is known to everyone, because these are weird phenomena which we are not experiencing on a daily life.
ChatGPT will help you.
Maybe. But it's not using that, right?
Of course it's not using that, but it can explain you what the term means.
That's true.
Yeah, it's your hack in the taxonomy here.
Smart idea. Never thought about this. And so basically and because of using these kind of physical phenomena, you're broadening the spectrum of what you actually can use for processing and generating data.
So in simple terms, I would say there's some super complex mathematical models known to the quantum mechanics world. And you apply that for complex information or, like, let's say, compute problems. And this is what the whole science is about.
That's true.
Okay. As this sounds quite fantastic and futuristic, it gives me a straight idea why quantum computing is not our topic of today. We rather speak about something that is way more realistic and is actually in a chip that is being shipped today, a photonic chip built by Q.ANT, your wonderful company in Stuttgart. What is photonic computing, and why the heck do we need light instead of photons instead of protons? So light instead of energy. What's the advantage?
Okay, so the fundamental idea of the chip technology we developed is that instead of electricity floating across a chip, we use light. Now, what's the great thing of light? We can observe this in the studio. Once you turn on the light bulb, light is propagating. You don't need to push it. So it's because I'm a physicist, and maybe there is some physicists among your audience. Light, or the fundamental elements of light, the photons, belong to the category of bosons, while electricity belongs fundamentally to electrons, and the electrons are fermions, which you have to push. So you need a potential, you need a voltage in order to create a potential, and then you push electrons across a chip against a resistance.
So wait a minute. Because somebody needs to kick the butts of those little protons all the time, the electrons all the time, the butt heats up, and that's why the chips always overheat, while the light chips don't need that and they stay cool?
Yes, that's a very easy explanation. Yeah,
super cool. I just got my elementary grade explanation. Okay, very good. So far, I can follow. Go ahead. So there is an advantage. We get it. There is no heat, no butt kicking of electrons.
That's the first advantage.
Okay,
there are more.
Okay.
The second one is light is a particle, as we explained. Ignore this for a second. We are not in quantum mechanics or something, but it's also a wave. It's an analog wave propagating at ultimate high speed. There is nothing faster than light,
as far as we know.
The physicists would say, then we would just redefine that this is the fastest we know.
Okay, point taken.
It's a theoretical concept, right?
It's okay.
But the The point is that basically a light propagates at the speed of light through the material, offers out of a sudden the possibility to not build a digital circuit, but an analog circuit. That's the second fundamental feature that we're exploiting. Now, in principle, you could do this with electricity as well, but you already, and we already endeavored, that you're pushing the electrons against the resistance. Things are heating up uncontrollably. And what happens is that you're adding unwanted noise to your electrons, meaning that the analog computation with electricity is imprecise. It has always this noisy error on top. And in the end, your computation is worthless.
Okay. Now, in high school, I have learned that turning on the energy, off the energy, etc., creates this 1010, this binary code, right? The basis of all our computers. With the light flowing and waving all the time, what does that generate? Also zeros and ones?
No. That's exactly the point and the main differentiator. So the semiconductor industry was very smart throughout their existence, and they exactly took advantage of that. It's very easy to turn off and on electricity, and so they created a digital alphabet. 0, 1, and depending on how many zeros you want, you add into a row, you can either encrypt characters or any other things.
Clearly.
Right? But everything relies on that a certain type of currency jumps above or is below a discriminator. 0 and 1.
Clear.
Okay. And with this, we came quite far. Now, the point is how much...
Well, it's a bit idiotic as well, right? Because this means it's just linear mathematics. And if you have nonlinear mathematics, you crack it down to linear problems, and then you toast your GPUs.
Yes. The question is, okay, if it's allowed to talk in that language, then it's even easier.
Yes. We want to have fun and learn something.
Okay, so, but that's exactly one of the problems with the digital industry, because if you observe what a computer does, a computer is a tool. It's a tool that basically tries, or it helps, it supports us humans to overcome some weaknesses.
Yeah.
So what can a digital computer excellently do? It can crunch numbers, because the binary encryption is much more powerful than our decimal system. By just having a binary number and shifting it for one position, you already can carry out a lot. So for these linear operations, what you said is probably one of the most elegant way to compute math. This, by the way, was solved in 1967 by inventing the calculator. Since then, we try to convince the computer to act more like a brain.
Right. While still giving him the basics, fundamentals of a calculator.
Exactly. So, I mean,
you get the point. That's quite stupid.
I mean, we don't have any better solutions. So
well, yours is not better. I was waiting for the point why the photonics is now cracking it.
Because I'll come to the conclusion. I mean, the world currently is looking with great joy on what we call artificial intelligence. But the artificial intelligence that we currently are seeing is something that's generated by a binary system. And we want to copy the functionality of the brain. And without being now a scientist, but just an observer of our human world, we would clearly see a human wakes up in the morning, it has a coffee and a roll, it eats some pizza for lunch, and then maybe some dinner, whatever. And then we look on what's currently happening in the data center, how much energy is used in order to train neural networks, and how long it takes just to do simple jobs to differentiate between a cat and a dog. So we see that there must be something inefficient, and it's not stupid, but there is no better solution currently, or till Quant realized the processor, because it's the digital nature of these circuits. Now, what we can do is we have an analog circuit. An analog circuit is you can see it like if you want to carry out a certain type of function, you don't need to translate this into 0 and 1s. You can just use it as you want to use it from your mathematical calculus. So you're just giving up the translation from, hey, there is a certain type of equation. What's the translation? Books telling me, I need to have this sequence of 0s and 1s. And now I start basically pushing currents across a resistance throughout a circuit, generating some gates, and try to somehow realize what the functionality in the analog world is. We just have direct access now to these analog functions.
So with the analog function, you can basically calculate natively nonlinear mathematics.
That's why we call it native computing.
Cool. And with this native computing, you're obviously faster.
We're faster in certain type of computations.
So in the world of complex AI models, like in pictures, videos, anything where we know from ChatGPT it's slow, right? Generating a picture is a nightmare.
Yeah.
Plus they never look like, I tried sometimes some cool pictures, right, I could use for business. The guy never looks like me. It drove me crazy. Anyway, so I hope for a better solution here. If you think a bit ahead, I know you're working left and right, front and center, and so many different research projects with hyperscalers. There's big tech giants reaching out to you. Half the world likely wants to invest after they have read about the round, which was one of the biggest, and congratulations, one of the biggest Series A's in deeptech I've seen in Germany in a long time. What's coming next? What's basically on your bucket list of items to solve besides internal, ramping up organization, hiring the greatest and smartest people? We all get that. More on the technical and business development perspective. What will you tackle the next?
You already mentioned this. So there are solutions for first steps into AI. This is what we call large language models, and I would say they can be improved, right? There might be smarter ways, but the semicon world has solved this and solutions exist. What we are focusing on is exactly what's the next big thing in AI. Mm-hmm. You already gave a hint to that. In our core belief, it's going to be way more on pictures, on audio, on all these kind of things. And I see this from the ultimate perspective of what we want to achieve with this type of technology. We want to have a better us. We want to have a better human that basically replaces some of the hard works that we do on a daily life with the human intelligence. Now, it's, in my opinion, unlikely that we can reach this with the digital industry, and it's unlikely that we only reach this with speech and language, because the human body has 5 senses. We observe things by eyes, we hear things, we smell things, and so on. All these other senses are way more analog than speech, because speech has 26 characters. It's, from a mathematical point of view, rather simple. Nevertheless, it's great that we have now large language models. And this is the other senses, namely pictures. That's what we currently observe and where we focus with our technology on, because we see that the way we compute is much more compatible to solve very fast these pictorial-driven AI cases. And for instance, realizing use cases, text to instantaneously video. So you're bored on Sunday evening because the television linearly doesn't stream what you want to stream, and you think, I ever thought about the following movie and no one has produced it. You write your plot and instantaneously your movie is generated. Other imaginations, think about the gaming industry. How about if you had an infinite game where you decide what the next steps in the games are and an AI is just generating the game?
Or I might have just my virtual pets with me wearing my AR glasses because I'm geeky enough to find that cool.
Maybe.
Okay. Fun stuff coming up. You guys are hiring globally?
Yes.
So if you're smart, and I mean killer smart, you might want to apply. I'm not sure what kind of profiles you look for.
Only the smartest ones.
But mostly software developers? Hardware guys, you have a lot.
We have hardware. We need on the hardware sector, we're maturing, so we need professionals that support us on growing from the prototype and early product status to the matured product status. The next big things are, as you said, are going to focus on the software ecosystem. The goal that we have, and that was, if I may say, the first remarkable thing that we demonstrated. We created a new processor, but this new type of processor is already seamlessly integratable into existing compute architectures. We are also fully compatible with the software libraries that are out there and commonly used, for instance, for the generation of AI, like PyTorch and all the other libraries. The point now is we need smart software developers on the one side understanding the advantages of these processors and creating software on the other side that dedicatedly takes benefit from these new functionalities. That's what we are searching for.
So if you're down for, building your next product, your next killer application, your next unicorn, you might want to think if it's a case that runs better and more efficient on Q.ANT's chips, on Photonic chips. You'd be definitely faster than the rest of the world. You might benefit both from each other. It was amazing speaking with you. Thank you, Michael. Thank you for joining us here in Vienna. I hope you guys enjoyed this as much as I did. You don't forget to subscribe our channel and please tune in for our next episode. Take care, guys.